All right, it's 12:30. Let's get started. You can see all the distinguished faculty here today. You can see that we have a very famous speaker with us today. Dr. Vasilis Marmorelis is no stranger to BME. He was here way before all of us were here. He was in the among the founding members of the department. And so Vasilis started off with a bachelor's degree in electrical and mechanical engineering from Greece, National Technical University of Athens. And he came to the States, did his graduate degrees, master's PhD at Caltech in what's called bioinformation systems at that time. And then he joined USC as a faculty member. He has, as assistant professor, rose through the ranks. He's been the principal investigator of this center that we have at USC called the Biomedical Simulation Resource since 1985. It's been renewed 5 times. It's one of the longest running centers in the US or in the world maybe in computational bioengineering. Vasilis also, well, a few years ago, well, let's see, maybe 10 years ago, he veered off in a slightly different direction and started to look into ultrasound imaging. Then he decided that he wanted to go and build something, so he took off some time, went to Europe to develop this new thing called novel technology called multi-band ultrasound transmission tomography, right? MUT. And right now it's in clinical trials, and so he's coming back here to do the other work that he loves, which is computational biomedical engineering, and he's going to talk to us about that today. Vasilis?
Thank you, Michael. I need to wear this.
Yeah,
Well, hello, everybody. It's truly a pleasure to be here and have an opportunity to talk to you about my work. Michael just, first of all, thank you for your gracious comments, and also he just made me aware of the fact that I'm being recorded. This is something truly new for me, and I promise to not to make any comments that are not politically or academically correct, which is something I do have a talent from time to time to do. I was told that also the time limits of this are quite specified, 1 hour, which is another novelty with me and a constraint that I'm not sure I can live with, given the fact that I am always late, and both in starting and ending my lectures. I do have a large number of slides because I decided to give you an overview of my work of the last 30 years or so. Naturally, I ended up with a large number of slides, and therefore be prepared. I would say fasten your seatbelts before we start, because we're going to go a little fast in this. Clearly, I would like to keep you with me throughout this, and I would like to respond to questions, but the pace of my presentation may not allow for too much interaction today. Nonetheless, I would be, of course, available and happy to answer any questions you may have after the talk, and at the end, of course, if we have time, which I doubt. So without any other delay, I will get started. And the title of the talk is quite generic. Of course, one would expect me to talk about modeling of biomedical systems, because this is what I'm known mostly for. And the addition of the analysis of signals alludes primarily to my work on the ultrasound tomography that Michael mentioned. And I will present some of those results as well. I like to start with an excerpt from Hippocrates. Naturally, you know, of course, the root of all wisdom is from Greece, right? Ancient Greece. Going all the way back to the 5th century BC, that in medicine one must pay attention to plausible theorizing, not to plausible theorizing, but to experience and reason together. This is a statement which essentially should be understood by all of us as the preponderance of the importance of data as opposed to simple theories. This is not to put down theories, because he says, I agree that theorizing is to be approved, provided that it is based on facts and systematically makes its inductions from what is observed. So the inductive way of scientific method is what is really the essence of this, and I'm subscribed to this, and I want to impress this audience with the same idea, that we really have to pay primary attention to the data. This is important because the approach I'm taking with my colleagues, Ted Berger and others, is primarily inductive in its mathematical and philosophical underpinnings, data-based. Another quote from someone you all know more contemporary, from the previous century, Albert Einstein, that explanations of natural phenomena must be as simple as possible. We all agree, a simple explanation is the best, but, he says, no simpler. Which goes to the fact that it's a very important fact that, in fact, in seeking simplicity, we must not deprive our problem from its essence. All too often, people develop contrived situations which they can study, but they do not really get any answers that are interesting. So I think those two quotes from these famous minds of previous times are important for all of us to remember, and I chose to start with that. Now, this is a list of the areas of biomedical system modeling that I'm prepared to briefly talk about today. Database versus hypothesis-based modeling, parametric and non-parametric, input-output and closed loop, static versus dynamic, linear versus nonlinear, stationary versus non-stationary, multivariate and stochastic, and point process systems, which is relevant to neural systems communicating with spike data. In all of those, the model specification, estimation, and interpretation issues are, of course, paramount. In the area of advanced biomedical signal analysis, I have created this list. The red highlight tells you why I use the adjective advanced. In the high order temporal spectral structure, not just second order, which is what most people are accustomed to doing, non-stationary spectral analysis as opposed to the classical stationary analysis we all know, like Fourier type of transforms, point process filtering and spectral analysis. This again alludes to neural data, non-Gaussian statistical analysis as opposed to Gaussian, which is most common, and multimodal ultrasonic tomography, which is the technology that I developed in recent years. Computational and mathematical modeling in science. Generally speaking, modeling in science is essential because of at least these four things I have on this slide. Organizes quantitative knowledge, summarizes the observed data, allows rigorous testing of scientific hypotheses, and enables the design of effective control strategies. One may find more, but this, I think, is a fair summary of the four primary reasons why we like and we must do modeling in biomedical, in life sciences in general. I must say, in looking at Don Marsh, who's in the audience, that much of this conceptual framework, which I consider still rather fundamental in my thinking, was formed and developed when I first came to USC, and I had the benefit of interactions with people like Don Marsh and Fred Grodins and Gene Yates and George Moore and the others who were at the department at the time. And I think we should be truly proud for having created that foundation, and hopefully we can carry forward. On the next slide, I simply give you an idea of how my work has proceeded, from methodology development to scientific applications to clinical applications. And the current thematic thrust that I have are modeling of multi-input neuronal activity. This is work done with Ted Berger and his associates. Multivariable homeodynamic autoregulation, and physiological control and functional neurosurgery. In terms of application areas, the golden highlighted are the current, the central nervous system. Again, this is the ensemble neuronal activity work. The cardiovascular system, cerebral flow autoregulation, endocrine metabolic There we're looking at glucose regulation, and finally medical imaging, the new technology we talked about earlier. In earlier years, I had dealt with sensory systems, the renal system, visual-motor system, and respiratory system. In the interest of time, obviously, I will not be able to cover all this, so I'll concentrate on the more recent work. This is a simple conceptual slide of the system or model conceptualization. You have, in general, you have a number of variables in nature that you observe, and you measure some of them, and you typically ask the question of whether there is a causal relationship between those variables, and if so, what is it? Can you quantify it mathematically or computationally? And typically we follow two ways, either the input-output formulation or a closed-loop formulation. In the input-output formulation, you have a situation where you consider the variable A in this diagram as the input and the variable C as the output, and you try to figure out what the causal relationship is between those two. Or in the closed-loop formulation, you observe, let's say, B and C, and you try to figure out how B and C are interacting with each other in closed loop.
Professor?
Yes?
Can you point to the smartboard instead of the projector?
This one. Yes, thank you.
Thanks.
This is, now we'll follow a few examples, quick examples of systems that I have dealt with, just to give you an idea of how we formulate the modeling problem. This is from the early work on the retina. On the left, you have a schematic of the retina with the various neuronal layers. And on the right, you have the signal flow diagram going from light stimulus all the way to ganglion cell output. Naturally, each one of these slides deserves a lot more time than I give it. I apologize for that, but it's by necessity I have to be brief and quick. This is a schematic of the hippocampal slice that this work done with Ted Berger. Again, schematic of the slide and a signal flow diagram below, which essentially indicates to you where we choose to consider our stimulus or input or our response, our output, or the closed loop relationships that exist there as well. More on this will follow, of course. This is a schematic of the cerebral blood flow autoregulation problem. Again, the complexity of these connections is impossible to absorb in a few minutes or even in a few days. And there is more in reality than that. The essence of this is that you observe variables. In this case are the yellow highlighted variables: arterial blood pressure, cerebral blood flow, and arterial CO2 tension. And you try to draw the causal relationships among them. This is a schematic of nested loop interactions in the endocrine metabolic problem I talked about. This is the relationship between blood glucose, insulin, and free fatty acids. This is based on some data collected in the lab of our colleague Richard Bergman. This is a final example, introductory example of a multivariable modeling problem. This one done in the Ted Berger's lab in collaboration with Dong Song and Sam Detweiler at Wake Forest. And here you see the hippocampus schematically with a multi-electrode array which records the neuronal activity at many different sites. And then you try to answer the question, what are the relationships that connect this, the activity of these neurons, both in an input-output or in closed loop. This slide is meant to describe to you how I see the data-based input-output non-parametric modeling approach that I have followed, basically, evolve through time. In the past, we dealt a lot with the question of Volterra-Wiener modeling in an input-output context. At present, we're using expansion-based Volterra-type models, and more details will be given in a minute. And in the future, we're looking towards creating compact multivariable models that obviously will address far more complex situations of physiological systems, including closed loop. In the way of background, this is a slide about the Volterra model. This is the basic functional relationship that is due to Vito Volterra. It's at least a century old now, who essentially put across the idea that you can always express the output variable of a functional relationship between two variables as a functional expansion. And this functional expansion, what's good about it is that it represents a canonical representation. In other words, it's true for all systems of a very, very broad class. How broad? I would say 95% of the physiological systems will fall into it. So it gives you a canonical and general framework to work with. In this Volterra approach, where you map an input past epoch onto an output present value, the critical role is played by these functions K1, K2, etc., which are called the Volterra kernels. These Volterra kernels do you think I can get some water? Is Marcos here? No. Okay. Doesn't matter. These Volterra kernels are the descriptors of the functional characteristics of the system. So if you know these kernels, basically you know everything you need to know about the mapping from the input to the output. At the same time, those kernels now attain an importance in terms of interpretation because they contain all the functional information about the system functional characteristics. And they form also a hierarchy with regard to the degree of nonlinearity. For instance, the first order term is the familiar to most of you, I believe, convolution integral of linear systems. So the first term is the linear term, if you wish. The second term is a quadratic nonlinearity. The third term, a cubic nonlinearity, etc. And you can go all the way up to the order that you deem necessary in your particular system. The main problem with this approach, aside of its mathematical apparent complexity, because it's only apparent, it's really a very simple thing after you stay with it for a few hours. The main problem that remains is the so-called curse of dimensionality. In other words, the fact that the number of free parameters in this model is quite large for high-order systems. And we have dealt with that, I think, quite effectively in recent years. This slide is meant to give you an idea of what we mean by nonlinear interactions. It presents two impulsive inputs, the respective outputs, and then the response to the pair of those impulses. And the difference, which is shown here with dashed line, is the nonlinear interaction. That nonlinear interaction, in this case, is second order because it's between two impulses, is represented in the Volterra formalism by the so-called second order Volterra kernel, which is essentially a three-dimensional function, a surface like this. Each point at this surface measures or quantifies the interaction between two input values separated by those time lags. The Wiener theory of nonlinear system identification builds on the Volterra foundation to further propose the use of a white noise input in order to interrogate or probe into your system effectively. Again, I apologize for being so quick and dense on this, but literally each one of those slides deserves probably an hour itself to do justice, but I'll try to capture the essential aspects of it. Wiener said if you're looking at a nonlinear system, you try to understand it from input-output data, the input you should be using is a white noise input because that's an extremely variable input and will test your system under all possible conditions. If you use specialized inputs, such as most people did at the time, meaning sinusoids or steps or impulses, you're only asking your system a specialized question. Therefore, you're extracting only limited information. You have to probe it with a white noise input. It's a tremendous proposition. It helped our thinking a lot. We have made that into a much more practical proposition in recent years because the use of white noise is somewhat impractical. And Barlow, thank you very much. You're great. And we now come to the point to appreciate that not only we can use band-limited versions of white noise, that was an early realization, but the fact that it is probably best to use naturally occurring stimuli which are broadband by nature, and therefore they're adequate for our purposes here in this modeling. But Wiener's contribution was critical in this regard. I dealt as a graduate student and a young scientist with this quite a bit. This is the first book I published with my brother Panos. This came out in '78, believe it or not. It's 32 years. You can tell from the beaten up cover that it has been used a lot. These are collector's items. It was translated in Russian and Chinese. It was very interesting for me to see my last name in Chinese. I still can't figure out if I were Chinese how I would be able to write this every time and so quickly. It's incredible. And I have a number of questions from my Chinese colleagues to ask them how they came up with that as a translation of my name, but that's for another time. So this book summarized the initial work we did on this approach. And here I give you simply the result from the first application ever of this approach, which was published in Science in 1972. This was done by my brother Panos and Kernel at Caltech. And this shows the first and second order kernels of ganglion cells from the catfish retina, subjected to white noise light stimulation. I show this for historical reasons. This is also a slide for historical reasons. It's Kernel's utilization of the second order kernels, shown here as contour maps, to classify amacrine interneurons in the retina, and also assign functional meaning to those interneurons. As you see here, this is a differentiator essentially rectified. So this kind of functional information can be extracted from the kernels if you spend some time analyzing them. Some of the key issues in the Volterra-Wiener modeling was the model compactness I already mentioned, the data requirements, estimation accuracy, computational efficiency, physiological interpretation, an issue that still remains with us, and its relation to compartmental or parametric modeling. I can say that we have dealt with the first four quite well. We're working on the fifth one and the sixth one currently. Extensions of the Volterra-Wiener theories. This is extensions that my colleagues and I made over the last many years. The two-input modeling, the multi-input, multi-output modeling, which still continuing, spatio-temporal and spectro-temporal modeling, likewise continuing, non-Gaussian and non-white inputs, that's done pretty much, non-stationary nonlinear modeling, also in progress, and spike input, spike output modeling. The journey, because it is really, it has been a journey. Starting out with Volterra, circa 1930s, the book, actually he did this work early in the 20th century, Wiener in the mid-50s, Lee and Setson in '65 with the cross-correlation technique, which was a pivotal point. I put my name ostentatiously, I guess, here along with the others, but nonetheless, as contributing to the kernel expansion technique. Of course, many others have contributed to this field, including Tedberger and others. And the principal dynamic modes, which is work, my most recent work summarized in a recent monograph I published in 2004. These are just volumes that contain work on this subject published over the years by the BMSR that I edited. And this is the monograph for which I'm rather proud, and I have to show you this commercial. This essentially, up to that point, summarizes in a rather comprehensive manner the work we did up until 2004. It contains the essential element of what you will hear more about, which is the principal dynamic mode analysis. The advocated approach is pretty much what you already heard, so I will skip over the slide. One key methodological issue has been the estimation of kernels via base expansions, which is described mathematically here. This has led to tremendous efficiencies, the way we estimate and represent the system model or kernels. We use the Laguerre expansion basis in most of our applications. A further step to this line of thinking is the principal dynamic modes. And this is a schematic of what we mean by principal dynamic modes. Here we have the input-output relation written as a series of parallel cascades of a linear filter, which will be called heretofore, from this point on, principal dynamic mode, followed by static nonlinearity, which will be polynomial. What's important here is you separate the dynamics from the nonlinearities. Some of you may not be able to appreciate that at this point, but believe me, this is a tremendous breakthrough, in a sense, or simplification of the problem, as you will witness later with some examples. A related spin-off of that work was the Volterra equivalent networks, in this case the Laguerre-Volterra network, which essentially are network representations of the PDM model. The multi-input, multi-output model. This is what what we have been using in recent times to. It's pointless to go through the math on this because we don't have the time. Early applications. A list of early applications pre-95 here: sensory systems, visual and somatosensory, respiratory mechanics and gas exchange, the renal blood flow autoregulation, we did with Don Marsh and Kitson, visual motor neuromuscular control at Markham's lab at UCLA, spectrotemporal laser induced fluorescence with Grantfest at Cedars-Sinai at the time. I will choose from this to show only one example, which Don will probably recognize. This is the PDM model of the renal autoregulation that we came up with. Finally, we were able to extract two PDMs in this system, which corresponded to the myogenic reflex and the tubulo-glomerular feedback. These were concepts that the physiologists had up until then, but were not able to quantify, and we were able to quantify them and correspond them to these two PDMs. And this is the two-input nonlinearity associated with these two. Now, what does this do for you, you may ask? Well, what does this do for you is encapsulates in a very relatively simple computational form all the functional information of that particular system. That's tremendous, because it gives you predictive capability for control purposes, or gives you scientific or diagnostic capability in terms of how these things look. For instance, someone who does not have a myogenic reflex or it is impaired, it will show up on the respective PDM. So you can use it for clinical diagnosis if you so choose. Current applications include the work with Ted Berger, neural dynamics of the hippocampus, cerebral flow autoregulation with a group in Texas, the Insulin-Glucose interactions with Richard Bergman, and neuroprosthesis also with Ted and Sam Deadweiler. Let me give you another example from cerebral autoregulation. This one is the outcome of analysis of real data that we did with George Mitchell, my former student, Rong Zhang and Ben Levine. In that system, we came up with 3 PDMs. What I want to draw your attention, because obviously I cannot go into the details of this, is that we're able to identify specific resonances in these PDMs, which now attain physiological meaning. Some of them are connected to the sympathetic nerve activity, some on the parasympathetic, or so we think anyway, some on the CO2 interactions, nitric oxide endothelial mechanism, or the respiratory sinus arrhythmia effects. Again, the idea here is that if you have a model like this, you can quantify these aspects of the model, and then you can make clinical use in diagnosis. You do this in normals, we do this in patients, you see what's different. You can diagnose, or you can monitor the evolution of disease. Now, this is a 2-input example of the same system, where the second input now is CO2. Previously, blood pressure was the input. Now we have blood pressure and CO2. The output remains blood flow. And the take home from this is that, in fact, both the pressure and the CO2 contribute to the total output, which is blood flow. But also there is a cross-interaction term, which is important. Interaction between CO2 and pressure. I submit to you that there are no other methods that I'm familiar with that can get you this result in this world at this time. So the ability to get into cross-interactions is a very important strength of this approach. The scientific and clinical objectives of the cerebral autoregulation study is what I already said. Basically, use them as biomarkers for any number of diseases you choose. We're looking at hypertension, Alzheimer's, and mild cognitive impairment at this point in time with data from the University of Texas. And what we hope is to be able to tell you in a few years that people can be diagnosed for any of those by developing the PDM model for those pathological states and comparing it to a normative database, and be able to tell what's wrong, how wrong it is, how severe, how the patient responds to drug treatment or other treatment by restoring that functionality, etc. So the implications from the clinical point of view are immense. This goes, of course, under the evidence-based medicine, which is certainly the direction of the future. The working hypothesis here is that a neurodegenerative disease will affect the manner in which the autonomic nervous system autoregulatory action is exerted in its subject. I do feel like I'm in a race, of course. On the neural side, my work with Ted Berger occupies a major part of my activities and can be roughly classified in three areas. One is neural interactions in hippocampal slices. The second, the multi-input, multi-output modeling in neuronal ensemble activity in the behaving rat. These are data coming from Wake Forest, and we're trying to look at learning and memory formation. And the third falls under the hippocampal neuroprosthesis category. I will try to quickly give you an idea of those three areas. This is the basic math we use for the so-called Poisson-Volterra kernel estimation using the Laguerre expansion. This is a photo of the hippocampal slice indicating in this example of a dual input single output model, we stimulate the two parts of the perforon path, the lateral and the medial, indicated as green and red there, and we record the response at the granule cell layer in the dentate gyrus right here. And these are some of the data. And by doing the analysis, which is along the lines of this mathematics, we get results such as this. This representing the first order kernels, these are the second order kernels in this particular case. Again, recognizing this is impossible to absorb in detail, just as a visual, I offer to you that we get this kind of results. Now, all that complexity you show with all those kernels can be condensed functionally to these three curves, which are the PDMs for this particular system. These are the three PDMs that come out of that data, which again, and I want to stress that once again, represent a common global coordinate system for representing all those kernels for all experiments. So you understand now, you can represent all your kernels using those three functions with linear combinations, of course, of those three functions. Okay? That simplifies matters incredibly. And of course, we harbor the aspiration and the ambition to eventually be able to point to specific biological mechanisms that are associated with each one of those PDMs. For instance, the black one could be AMPA, the green one could be GABA, and perhaps the red one could be NMDA. But that work has not been completed yet, but we're hopeful to be able to complete it soon. This is just a slide on the neuroprosthesis that Ted has been pursuing for years, and I have been helping him with. This is a successful FPGA model of neuroprosthesis for the hippocampal slice. This was a success story. It worked out well. We're trying to do now the same for the hippocampus of the behaving rat in vivo. This is an example of from the hippocampus as well. This is in the behaving rat, so this is in vivo data. One neuron from CA3 talking to a neuron in CA1. These are the kernels, and these are the agreement between the actual output and the model prediction. As you can tell visually, it's very good. In fact, for most people, too good to be true. Likewise, you can extend this to multiple inputs. This is an example of three inputs going to one. This is three CA3 neurons talking to one neuron in CA1, showing the various model predictions. The moral of the story here is the prediction improves as you include more inputs if that output neuron talks to more input neurons. Again, we saw this schematic earlier today, but I'm showing it again to make the connection. Here, with the multi-input, multi-output setting, we're recording at many different neurons in CA3, and we try to develop the causal relationships with neurons in CA1, multiple of them. So that mapping we develop along the lines of the Volterra-like modeling, which is shown in this math. And this is an example of simply one first-order kernel, or I will call it spatio-temporal kernel for the purpose of this, and the comparison with trigger correlation, which has been for a while a competitive, rather an alternative competing methodology. It shows you how 10 input neurons map onto a single output neuron. This is actually real data, again from the behaving rat we talked about earlier, the hippocampus of the behaving rat. And this is the result we get using the Laguerre expansion here, or using the trigger correlation. It's not only visually unappealing to look at the trigger correlation result, it is also not very useful, because if you attempt to do prediction, this is the result you get. Top trace is the actual output, second trace is the output from our model, rather the prediction from our model, and this is the prediction from the trigger correlation model. The trigger correlation gives you essentially, if you wish, a bundle activity, but not a specific timing of the spikes, which we get with our model. This is yet another example from the same MIMOS system, and the long list of first-order kernels, second-order kernels for, in this case, 7 inputs talking to 5 outputs. The purpose of this is, of course, not for you to absorb the detail, but to show you that, in fact, we have done it for multiple inputs and multiple outputs. And this is the kind of connectivity maps that we were able to develop in the rat hippocampus, where these lines, the strength of the line, the thickness of its line, indicates the frequency by which each one of those connections was observed in various experiments of the same rat. This is the same rat. The 4 pairs are 4 different tasks, indicate as left sample, right sample. These are different behavioral tasks, and these are the 2 left and right sides of the hippocampus. So you can develop, if you wish, functional connectivity maps with this technique, which can be of great importance in neuroscience in general. This again is one such example. Only here we show also the PDMs that come out of these specific 4 output units. I am pushing the theme of PDMs because I do feel and believe that it has great promise for the future in terms of compacting our model representation. The scalability of the MIMO model is an issue that we intend to tackle in the future by using PDMs and other techniques, and be able to handle multiple inputs, large numbers of inputs and outputs. Ted and I have come up with this additional idea, which is called Boolean Volterra modeling, which is actually the most obvious thing to do in neural systems, but has not been done for some strange reason, and that is to use logical operators instead of real number operators to represent input-output relations. Since neurons talk to each other with spike trains, which are binary signals, 0, 1s, why not use Boolean operators? And that's the idea. We use Boolean operators and, or, and not to not corresponds to inhibitory connections and to excitatory, nor is various alternatives you have. And we build a Volterra-like hierarchy of multiple interactions using logical operators. I wish I had more time to go into details of this, but I find this an extremely attractive concept, which so far we have shown to work fine in simulations and reasonably well with real data, and we're in the process of testing it with real data. This is an example of a simulation example of such a relationship, the input, the output. These are the Boolean Volterra kernels in this case. They're binary also, 0, 1s. And this is actually results from the data of the rat hippocampus. This is the real data. In the Boolean Volterra kernel, which is indicated here by the red bars, what you see is essentially the theta rhythm that is evident and prominent in these hippocampal neurons. The theta rhythm is around 7 Hertz. So these are separated by 140 milliseconds. The green spot here is an inhibitory lag we found in this particular unit, and in the bottom we have the Volterra kernel counterparts of this, just to see what you get if you use the traditional Volterra approach. And this makes the point why Boolean Volterra may be very useful. Here you have to remember only these two numbers, the lags of these two active red lines. Here you have to remember a whole curve and a whole surface. Computationally, that's a tremendous difference of with implications for, of course, implementation of neuroprosthesis and other analysis tools. I now switch to the problem of insulin-glucose interactions. Again, this is work done with George Mitchell and Richard Bergman. The schematic shows you the insulin I talking to glucose G. These are data recorded in a fasting dog at rest. And we try to get Volterra-type models for the A and B operators that mediate between insulin and glucose in a closed loop. These are spontaneous variations. We do not introduce any insulin. We're just watching what's happening in the dog's blood. Okay, so there are spontaneous variations of insulin-glucose concentration in the blood. And this is a mathematical depiction of that model. And this is the actual data. I think it's worth looking at just to get the feeling of how variable this data is. Top trace is the insulin, second trace is the glucose, and third trace is the free fatty acids in the blood. These are samples drawn every 3 minutes over 10 hours. So this represents 120 sample points. You understand this is not a trivial experiment to make, but Richard and his people were able to make it, and they have promised more. We only have one at this point, but we have been promised more. And we'll try to, I'll show you some of the results analyzing this. These are the PDM models that we got for operator A and operator B. Remember, A and B were the forward and the feedback loop in the insulin-glucose closed loop. PDMs, you read them the way we indicated earlier. The first two curves are the filters, like impulse response functions of filters. The second curves are nonlinearities associated with the respective filter. If I say that we can spend many hours just on this slide, I will not be exaggerating. Okay. This here summarizes potentially physiology of decades. And people like Don can appreciate, I think, that very much. An example of the same data, but here on the 2 input, 1 output case, the 2 inputs being insulin and free fatty acids, and the output being glucose. And here we try to get an idea of how the two insulin and free fatty acids interact with each other in affecting the glucose level in the blood. And the upshot of this is, and I don't know if you can read it well, it's in red, and it's that insulin sensitivity of a patient depends on the free fatty acid level. You see the free fatty acid PDM is positive, so if you elevate your free fatty acids, this will move essentially the operating point on this nonlinearity higher. You can tell that this nonlinearity is concave, so it has a diminishing first derivative, diminishing slope. And this insulin sensitivity, which is a term used clinically to indicate how much in each one of us insulin reduces glucose or assists metabolizing glucose, changes with the level of free fatty acids. Now, this is a direct quantitative indication that, in fact, the existence of more free fatty acids, perhaps in obesity or other pathological cases, reduces your insulin sensitivity. This is an issue that it would be no exaggeration if I say that hundreds of millions of dollars are spent almost every year in exploring. And here, you know, humble us, we at least get the first indication, because there's only one data set. So if this is repeated in more data sets and is consistent to some extent, this can have tremendous implications in that field. We switch to another issue. This is the synergistic use of data-based and hypothesis-based modeling. Most people in science are using hypothesis-based modeling. This is the deductive approach, where you postulate certain models based on the scientific knowledge you have up until then, and you try to formulate hypotheses and test them with the data. This is time-honored. is respected by all of us and has paid good dividends, especially in the physical sciences. Has paid good dividends in the life sciences as well, but not as good as in the physical sciences. What we try to say here is that we should use that, continue using that, but use it in conjunction with, synergistically, with the data-based approach, which is the one I just presented. Okay, let your data tell you how the model is likely to look, then test with that your hypothesis. So do both in an iterative loop, going from one to the other until you converge on a model that is true to the data and consistent with our scientific understanding of the system. Okay, so that's the main idea. That too is of tremendous, I think, importance for the future of science. Two cases that we have published so far is one with Dong Song and Ted Berger on the synaptic dynamics, and another with Mitchell and Markakis on infused insulin effects on blood glucose. I'll say a few more about that last one. It's easier for me to describe it. The first two equations that you see there are the so-called minimal model for insulin-glucose interactions in connection with the glucose tolerance test. These are due to Richard Bergman, a USC faculty, medical school, someone that Don Marsh actually recruited when he was chair in the physiology department, and who's worldwide known for this minimal model. That minimal model is minimal, so it can be extended. And one way to extend is to include a branch that accounts for the insulin secretion by the pancreas, which is this equation here. And the equation is the frame, then this frame is replaced by that frame. That's why I have framed them. Anyway, for now, for your purposes, imagine two hypothesis-based models, one called minimal model, the other called extended minimal model. And then you have our approach, which is data-based. So using our approach, we get the PDM models for the minimal and the extended minimal. And first of all, you compare these two. Remember, the data-based approach is canonical, means it applies to everything and gives you a common frame of reference. You can compare things in that. It's like a coordinate system. Okay, visually, what do you see? You see this PDM resembles in appearance this, but this is much faster than that, if you look at it carefully, in terms of the time axis. Also resembles that. So it's sort of like the minimal model PDM is an agglomeration of the two PDMs that you have in the extended model. And the respective nonlinearities, well, I'll leave the judgment up to you. But it looks like the nonlinearity of the minimal model resembles the nonlinearity of the second PDM of the extended model, but not at all the first PDM. Now, if you had a need to use this either in science or in medicine, which one would you prefer? Well, the more detailed one, because clearly this has more information. It contains the insulin secretion mechanism, which this lacks. All right, very good. That we accept, you may say. What's the next logical question? The next logical question would be, is this good enough for real data? You say, okay, so we need real data. So you have to jump through the hoops of getting real data, which is a very difficult process. And I'll show you this example, which is actually from a human subject. And these are the two PDMs from that human subject and the associated nonlinearities. It is not possible for you to retain the information from the previous slide to compare. I can go back and forth, compare the extended model there with this. Now, your impression should be that the PDMs are not that dissimilar. They are different, but not very different. But the nonlinearities are very different in the two cases, which is to say that the real data tells us that we have to do something with a hypothesis-based model. We have to modify it, we have to extend it, we have to do something with it to be able to explain the data. Okay, so that's really the main take-home message. This slide speaks to the fact that for the PDMs can be realized into differential equations through realization and impulse invariance methods. So for each PDM, you can have a linear differential equation, which is equivalent. Some people like to do that, people who are accustomed to dealing with differential equations of state spaces. I'll come to the one before last topic, which is the closed loop or nest loop modeling using homeodynamic modeling. The term homeodynamic is due to another former colleague of ours, Gene Yates, who is probably at UCLA still. I remember Gene talking about this 30 years ago. He had this concept that homeostasis is a powerful concept and true in physiology, yes, 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 but there's more to it. That physiological systems are not in a static state ever, but they're constantly in motion. And you really should be using a concept like homeodynamics, which means we retain a dynamic stability of the physiological system, but in state space, if you wish, not as a stationary point or stationary curve. It's a powerful concept. Again, deserves a lot more time than we have, but this is what I'm trying to capture here, and I'm very excited about this work. Essentially, what I propose is that we use a Volterra type operator operating on a number of variables, as many as you have measured, at the same time. So we make no distinction between inputs and outputs. They're all taken together. And finding V from the data, E is a residual type of thing, an agitator, a disturbance, or an innovation process. I call it anisotropy. Being Greek, you have the benefit of coming up with words that sound scientific. Anisotropy means lack of equilibrium in Greek. And essentially, if you're able to get this model, what you have is a true closed loop representation of your system. Here now you can represent oscillators, chaotic, potential dynamics, etc., etc. So this is a non-trivial extension of the Volterra modeling framework. And I hope to be able to report the results to you in the near future. I will skip over the estimation issues of the homeodynamic model in the interest of time. But essentially what you try to do is minimize the projections of your variables on the anisotropy variable. Kind of classic. And re-summarize where our work is currently heading in terms of applications. The neuronal dynamics in the hippocampus with Ted, the cerebral blood flow autoregulation with my colleagues in the University of Texas Medical School, and the blood glucose regulation in collaboration with Richard Bergman and others. In all three cases, you have multiple variables that are implicated in defining the function of the system. And how to deal with that multivariable context is the big challenge. And what we propose is, in fact, you do that in the context that was presented, and then we will have major impact on both science and evidence-based medicine. Now I'm going to the second and last part of the presentation. This is much briefer than the first, you understand? So don't panic. This is the biomedical signal analysis part. Non-stationary analysis is one section, and the ultrasonic tomography is the other section. I'll be very brief on the first one so I can spend a few minutes on the second, which is very dear to my heart. This is a result actually we got with Stan Yamashiro many years ago. We unfortunately did not continue this work. This was an unfortunate decision, but nonetheless the result stands on its own. This is non-stationary analysis of respiratory mechanics, and it shows evidence that in fact we can measure the respiratory mechanics in a time-varying context. The implication here is that you can do this functional respiratory function tests on patients that without asking them to hold their breath, which is very difficult to do. You have the subject breathe normally, and you collect your data, and you do the analysis, and you get your results. Okay, and now we come to the topic that, as I already indicated, has been very dear to my heart the last 10 years. This is a new imaging technology, you may say. I call it multimodal ultrasonic tomography, MUT. I got one T off. What is new about it is it is tomography, but using ultrasound instead of X-rays. That's good. We don't put all this radiation into innocent people. And furthermore, has a tissue characterization capability. Now, please try to understand how huge a claim that is. If in fact we prove we can do it, then we'll be able to tag individual tissue types without cutting up patients. The surgeons will hate us, but the people will love us. And we'll feel good about ourselves, of course, for doing something useful and important. And how do we do tissue characterization? Well, we base that on multi-band analysis or multimodal analysis. In this context, think of it this way. Each tissue type has a different way by which it attenuates ultrasound as a function of frequency. As you increase frequency, tissues usually attenuate more. Almost all tissues attenuate more. But the rate at which they attenuate more changes from tissue type to tissue type. The thought is, let's use that information. Because, let's say, a malignant lesion, God forbid, may have a different frequency-dependent attenuation than a benign lesion or a normal tissue of some type. In which case, we'll be able to tell from the new mammogram whether a woman has breast cancer or not. And we don't have to cut her up for an unnecessary biopsy. As an example, I think you understand the implication of this even beyond breast cancer detection. Okay, the first application is in early detection of breast cancer. The next application I'm preparing is on osteoporosis and bone quality assessment in general, but there are other potential applications. This work was initially supported by AMI between 2000 and 2005, which at that time interrupted its support, and it since then has been supported by a small company in Europe, Mastoscopia. Michael alluded to that earlier. And Mastoscopia has also supported the initial clinical trials there. This is how the prototype looks. Well, the woman, of course, lies on this bed, prone. The breast is suspended freely under gravity through this opening, and the scanning chamber is this guy that turns around, goes up and down. A schematic of the scanning configuration, classical tomography. The breast is immersed in a water bath, and these are the two ultrasonic arrays, transmit and receive, goes around, goes up and down, and does a full tomographic scan. One of the tricks that I was able to do because of my background is called excitation. So we don't transmit a single pulse like traditionally do, or series, but we transmit a pseudo-random sequence of pulses. The benefit of this is you gain a signal-to-noise ratio on receive, something we may talk about at a later time, and cuts down on cross-interference, which is a big issue we have here. Because each transmitter has its own pseudo-random code. Think of it as being the analog of what Qualcomm has done to cellular telephony. Okay? So you transmit with a different pseudo-random code, and the respective receiver knows that code and cross-correlates, and what that does is kills all the interference from the undesired interference from the other transmitters. This slide summarizes what is probably the most important part of this new technology, the multi-band aspect. In other words, for any physical slice of the object, you have multiple images, each image corresponding to a different physical attribute. In this case, it is different frequency bands. This is the sinogram you get from tomography, and this is the image. This is on a kidney, actually, ex vivo. So for each physical image, we have multiple images. For each physical slice, we have multiple images. So we can utilize them to understand that slice better. This is an example of from the kidney, 4 different frequencies. They contain different information. Of course, higher frequencies have higher resolution information. This again shows you that agrees with the basic anatomy we know on the kidney. This is a comparison of our technology with MRI and with optical. Optical means we cut it through and we took a photo of it. I'm rushing because I see the clock is after me. This is something we actually published in the New Scientist. It shows that we were able to do classification of the various tissue types in the kidney according to what would be expected. This is the pelvis, the calyces of the pelvis. This is the papillary ducts. This is the blood vessels, mostly in the cortex, but a little bit in the medulla. And this is the capsule, the renal capsule. I don't know if you've seen that, but we better look at it at some point, because Dr. Marsh is an expert in renal physiology in the kidney. This is a 3D reconstruction of the kidney. Again, this is ex vivo, right? This is a 3D of the papillary ducts only, one of those clusters. I can make this dance and work, but I don't have the time, animated. Now, this is a study on mastectomy specimens we did here, actually, at AMI. So we took mastectomy specimens from unfortunate women. We analyzed them with our technique. We did the characterization that I just talked about, and we compared our results to what the pathologist has marked. This is what the pathologist has marked. The dark area is invasive carcinoma, the bad stuff. The purple is benign changes, and the pink is normal. This is the actual photo of that slice of the mastectomy. And this is the punchline. This is the comparison of what the pathologist did here versus to what we get from our imaging technique. And you can see the correspondence of the invasive carcinoma, which is really the only part of interest here, is very, very good in this example. We didn't have that many. We did, I think, 5 specimens altogether. It's very expensive. We didn't have much support for it. But also, you know, the benign changes and the normal parts also correspond quite well. And let me come to the punch line, which is the initial breast images from the first clinical prototype. These are actually the first images from the first volunteer. I'm only showing 4 slices. We get many. These are 2 millimeters apart. These are attenuation images. And the red, what is known here as red, is shown as red, is the glandular tissue, is the mammary gland. The green and the greenish and yellowish cyan color is fatty tissue. The yellow is connective tissue. And blue, in this particular case, deep blue, is a cyst, is a benign cystic lesion, essentially. This just is a visual to compare with images I found on the web from CT mammography. That CT mammography is not normally done. Some did it and was kind enough to put it on the web so I can find it. I could not find anywhere else. Just to show you that it shows qualitatively similar results. The gland is the red, the blue and the green. The blue is the fatty tissue and the green is the connective tissue in his color coding. This is the first result where we saw a benign fibrotic lesion. It's this dot here that you see I have marked, which is dark red. Again, successive slices of that breast. And this is RI image, means speed of sound image. It's not attenuation. We can also image something based on the speed of sound, or the various voxels or pixels. This is a confusing slide, but I think it has its own utility because it compares MRI on this patient for one slice, of course. The MRI is here. The white in the MRI is fatty tissue. The inner core mammary will be able to appreciate that very quickly, is the gland and some connective. And this is how we look. This is, we try to emulate a little bit the gray scale image. Now, keep in mind the reason that this thing that looks like a bird is turning up here, its head, is because the MRI and our scan have the breast differently positioned. The MRI has it anyway. Ours is freely under buoyancy. So it takes a slightly different shape than what you get in the MRI through clear gravity. So you have a co-registration issue. This compares on another patient, an attenuation map with an MRI. And this is another patient where we were able to find a probable benign fibrotic lesion in this spot, 52-year-old woman. And this is the MRI slice for that particular woman where using DICOM, this identifies a fibrotic lesion. That's why I'm showing it here as verification or validation of the result. So, my friends, we do have an exciting year ahead of us. And it's up to you to make the best out of it where you feel like it. As far as I'm concerned, at this age I can say with great comfort that the life sciences and medicine offer tremendous challenges to us as a society, both in terms of interesting science, in the scientific questions, technological challenges, and using, of course, emerging technologies and methodologies. One of those fundamental methodologies, in my opinion, is that of system modeling and signal analysis, about which I talk to you today, and which, of course, I have decided to make the center of my professional life. The last slide gives credit to the many PhD students, postdocs, and faculty collaborators or associates I have had over the years. Thank you very much. I am on time, almost. Quite surprisingly. The chairman will tell me if I have time to take questions or not. Thank you. So it seems we have a few more minutes. Yes, sir.
Elaborate on parametric versus non-parametric.
It was very quick. I agree. I can. The term parametric is usually reserved for cases where we postulate a differential or difference equation. We used to be differential, now it's difference because we digitize or discretize everything. And the parameters refer to the coefficients of those equations. Oftentimes those equations tend to be linear, associated with nonlinear algebraic equations like Michaelis-Menten type of curve or sigmoid curve. All of those equations are postulated by the investigator on the basis of what the investigator knows about the system, and they contain free parameters, coefficients or otherwise, which have to be now estimated from the data. That's the parametric approach in our definition. Non-parametric is the way through the kernels that I traveled with you. So non-parametric because we don't have explicit parameters, even though it is true that is somewhat of a misnomer because in the end we parameterize the non-parametric kernels by doing kernel expansions, as I indicated. So when you do Laguerre expansions, of course you parameterize your kernel, right, into the Laguerre expansion coefficients. But the distinction as a term has remained because we find it convenient for communication purposes. Now, a close relative of the parametric model is the so-called compartmental model. In fact, most parametric models are compartmental models as well. Compartmental models are, of course, for the benefit of the audience, I'm sure you know, is that you segment your problem either functionally or structurally in segments, and you write equations for each one of those segments. And then you connect those compartments, I should call them compartments. That's why it's called compartmental modeling. And then you deal with your system as this whole of those interconnected compartments. That's a close relative of parametric modeling, usually contains, in other words, parameters to be estimated by the data. The classic problem here is, A, how you postulate this correctly, because you're guided only by your own resident wisdom. And two, the number of parameters tend to be quite large, and there are estimation problems that people have identified in certain cases. You avoid the second problem by going to minimal models. This is why our colleague Richard Bergman was so successful with the minimal model in glucose studies, because he condensed the model so much that only had 3 parameters, and then we were fine estimating them from data. But if you look at most models in this field, compartmental models, they have upwards of several dozen of parameters. So how do you deal with that? And so I hope I answered your question. I'll go to the next question. Francisco.
Very provocative. Thank you very much. I was just
Thanks.
wondering, if you use PDM modeling on the action potential, do you think you can recover the ion channel dynamics?
Yes. That's a brief answer, yes. I believe so. In fact, we have done that. No, we have not done that, and I want to do that. What we did there in earlier days is we did kernel analysis of the Hutchinson-Huxley equation, and we did a preliminary PDM analysis with a graduate student, which showed promise. That was unfortunately interrupted because she left, because her husband moved, the two-body problem, and that was left an orphan, remaining to be adopted and grow, which I intend to do, because you thought I value the importance of that. And this will help us also give meaning to the PDMs in connection with the hippocampus that Ted is studying, or other areas. So yes, although I do not have a published result, therefore I do not have a definitive result yet, the indications I have at this point in time tell me that it is likely to work in that. And that will be very interesting. Any other questions? All right. Well, I never thought I would have time left. But well, thank you very much for coming, all of you.